I welcome you to my talk, which will be about flex data for aquatic applications. So just to introduce a bit myself, I'm a researcher at the Alfred Wegener Institute in Bremerhaven. I'm leading there a group focusing on aquatic optics and also aquatic color remote sensing. I run this group since 2007, and I'm also a professor for environmental physics at the University Bremen. And before I started the group in 2007, I've been working as a postdoc 6 years at the University Bremen in the group of atmospheric physics and chemistry. And while I was working there more on mainly Skiamaki, a German atmospheric sensor with high spectral resolution, doing mostly the validation of trace cases, because I had a background in biological oceanography and optics in the ocean. We also tried Skiamaki for exploitation, getting more information on algorithms, innovative products actually for the ocean. And this is kind of the ground of some research ideas we developed, which could be attractive also for flex data to be used of. And since like 2005, we have been working on Skiamaki and then later on GOM2, like a successor mission, and also OMI, and lately on TROPOMI to exploit this originally atmospheric sensors also to get interesting information on the oceans. And with Flex, I think we will have a good opportunity to develop this much further and also go into other waters than just the open ocean. Yeah, so the work I present is all more or less published, and then some more ideas coming from myself. And it's mainly based on 3 PhD theses, Alexandra Volanin, Yulia Oelker, and Alireza Zadegi, which graduated now already quite some time, and also a postdoc, Tilman Dinter, who unfortunately died early in 2023, just two years ago in an accident. So I'm very thankful to their work, and we also had very good productive collaboration with the Institute of Environmental Physics, like the heart of Skiamaki, John Boros group, and also with some oceanic researchers from various institutes who helped a lot in the evaluation of our innovative products. So what can we actually observe from optical remote sensing? What gives us information on the ocean? It is that only the optical and UV light is actually penetrating the ocean, opposed to all other radiation, which is just reabsorbed in the first micrometers. So depending on the light-lit ocean, what is actually in the ocean, the light will change its spectrum. On the left side here in this picture, you can see like a more typical open ocean. So it means very low in productivity, low free-floating organisms like phytoplankton, which are green as plants are, and also very low degradation products of those. And the light which penetrates most is the blue light, and this is mainly because the absorption of water itself is so strong in the red. While if we are in more productive waters, this is more shifted to the green, and then if we have also a lot of interior, like degraded terrestrial plants, it would even shift more towards the red. So actually, with retrieving the signal of contributions of the light from the water itself, we can actually get information mostly globally on the productivity of phytoplankton. So how much is actually there in phytoplankton, and this is determined as its main pigment, the chlorophyll concentration. We can also get more information on phytoplankton, like different pigments, and we can also use the data set together with information on the light to get something like the global primary production. And it's important to know that, and it's like the basis for a lot of assessment of global fluxes. And it's also key for the marine food web, so for simulations of ecosystem functioning and forecasting. It's a very important data set. Unfortunately, we have a lot of processes which disturb the signal coming from the light, which is reflected at the sea surface and is influenced by the water constituents, so not only phytoplankton, but also dissolved organic matter which is colored, so degraded pigments or other particles. We have a big influence from the atmosphere itself. So about 70% of the signal is just scattering at the molecules in the atmosphere. We have the aerosols, which contribute and which are the most unknown finally in the retrieval to obtain then just the signal from the water. Also, if the sea is very rough, most of the data have to be screened out because you cannot actually look inside because everything is reflected, besides clouds. But clouds are also difficult for terrestrial application. And overall, the water is mostly very dark, so we really need a good signal to noise ratio to retrieve some information. So this makes retrievals more challenging than even for terrestrial applications. So just in summary, so most of this signal, which actually is part to the water reflectance and measured at the satellite, is far below 10%. At maximum, it's about 15% of the signal. So we need a really good methods for correcting for the atmospheric and surface effects. Okay, so the main target also probably for flex aquatic application would be phytoplankton, which is key to know more about phytoplankton. We already have a lot of satellite sensors in place, which can determine the amount of pigments of phytoplankton and also degrading products, but I think flex can add some more information. What is also interesting beyond just knowing the bulk of phytoplankton amount in terms of chlorophyll A concentration would be also to know more on the composition of the phytoplankton. So there are thousands of species, but they can be organized into different taxonomic, but also into different functional groups. So groups which influence differently the matter flow in the ocean and also the exchange with the atmosphere. So just a few words on those groups. We can have diatoms, very well known. They're quite big. They belong to the microgroup phytoplankton, and they have this silicate material. So they build up biominerals. They are actually forming most of the very, very large blooms, and they're mostly the blooms which form first. So if there's a lot of nutrients, they are the ones to grow fastest. And often they're not even eaten up all. So there's a lot of them sinking down, and we have a real removal of carbon dioxide in the ocean if we have strong diatom blooms. We have other groups of phytoplankton which can dominate. One belong to the overall group called haptophytes. They are in some ways also similar to diatoms in pigmentation, but mostly much smaller and have additional pigments. And they can either be coccolithophores, which have a calcareous shell, and thereby with this carbonate calcite plates around their cell, they counterwork to the carbon pump. So they're influencing the carbonate pump. And they build up often secondary blooms in the oceans, or actually when oceans have become warmer, we also saw them moving into areas they haven't been before. So there can also be an indicator of climate change. And we have another group called premnesiophytes, which are these algae which make like big foams, sometimes in the North Sea, and they also release substances which are precursors for aerosols. Cyanobacteria are also quite known, I guess. They can also form huge blooms, especially in the Baltic Sea. And some of them fix elementary nitrogen. So all of them have different functions, and we can have toxic algae blooms. And to differentiate the phytoplankton and have satellite data which help us to identify harmful algal blooms or benefiting blooms is a big advantage. And mostly the retrievals are based on looking at their different strength in absorption along the spectrum. And you can see now in this lower plot that most of these changes are actually happening probably in the wavelength range between 400 and 600 nanometer, while at about 65 nanometer, they all have a clear peak, which is like the second peak of chlorophyll A. And this is more homogeneous and can be used also as an indicator of chlorophyll concentration. Mostly in the open ocean, this light is already reabsorbed by the water, so the retrievals focus on using a band ratio or something similar or more sophisticated, but mainly using the blue to the green light ratio. So overall, these differences in the pigmentation can be used to actually resolve the contribution of different phytoplankton groups to the overall biomass, and then helping to perfectionize forecasting also for fisheries, but also for looking at historic data and climate change influence and so on. But also we have the problem that a lot of pigments are in common, not only chlorophyll A, but also some of the carotenes are in common. And it's quite challenging with inverse models purely based on analytical methods using radiative transfer to even resolve from perfectly atmospheric corrected data phytoplankton groups. But the last 15 years now focused heavily on exploiting even the current ocean color data, and we have succeeded in some ways, but I see some potential also here for Flex to contribute further. So just to show the difference between like a classical ocean color sensor like the ocean land color imager from Sentinel-3, which is probably currently the most sophisticated multispectral ocean color sensor, providing data also as Flex, and Flex will fly with it in tandem, so at 300 meters resolution, and providing spectral information at 10 bands in the visible wavelength range, which is the one relevant for applications in the aquatic systems. And on top, you can see the two Flores sensors from Flex, and for the water application, Flores LR would be the one which would be interesting, but it only starts measuring at 500 nanometers. So opposed to looking at the blue ocean and changes in pigmentation in the blue and even in the UV, we have to focus more on with applications for Flex in the green and the red spectral region. And I see still some potential to complement the classical ocean color fleet of products. So maybe the first one is we can definitely use this peak of the chlorophyll A at around 70 nanometers as a good estimate of chlorophyll concentration in waters where actually you have much more particles. That would be more meso or eutrophic waters. Probably also with the high resolution, we can get a good peak height here, but mainly the peak height would be used actually, this is the absorption, so we would see a dip. And we can also look at the sun-induced fluorescence. So sun-induced fluorescence from chlorophyll looks like this. So in red, you have the absorption spectrum, and you see the fluorescence of chlorophyll A is very close to the peak of absorption. But because Flex has this very high resolution, we can probably very well identify the strength of the sun-induced fluorescence. One has to keep in mind that in the dark ocean, so in the low productive area, it's still a very low signal because still you have not only the reabsorption from the chlorophyll itself, but also from the water itself. But with 300-meter resolution, we can obviously get much more precise than what we can with MODIS or ALGI, the influence of the emission of the fluorescence. With the broad multispectral band size, you only get that very vaguely. I will show later an example. So that is a potential. Besides, I think we could also focus on some information on the phytoplankton composition. So if you look here in the spectrum between 500 and 600, many of these different groups look similar, but especially this magenta and purple one have certain peaks which result from certain pigments called phycobilins. And these groups are blue algae, which are also quite relevant to form strong blooms and also sometimes toxic blooms more in the shelf waters. And also we have the group of cryptophytes, which has a less pronounced peak, here the purple one, which are more dominating in freshwater systems. And this could be a good way with the high resolution and covering the whole wavelength range with Flex to get more information on those. Based on the high spectral resolution, I would actually look for both for chlorophyll and for phycobilin fluorescence signals, and I will show some examples. Another example of looking at inelastic scattering effects is actually inferring how deep the light can penetrate into the ocean, and this can be done over certain spectral ranges. We have proven that for Skiamaki in the blue part, and I would see potential here for Flex in the red part. So in the following, I want to give some examples from the past where we developed methods and applied them mainly to Skiamaki, but also to some of the newer sensors. So just a few words to Skiamaki, because I guess most of you might have not heard of it. So this was an instrument which was also on board Envisat together with many others, like many atmospheric sensors, also the ocean color sensor, the predecessor of ALGI named MERIS. And it had a very high spectral resolution, but as I heard, Flex might have even higher spectral resolution, so 0.2 to 0.5 nanometer in the visible range. And it was measuring from the UV to the near infrared. And the pixel size was quite large, 30 by 60 kilometers, like opposed to 300 meters from Flex. And it was for atmospheric purposes. So it was not only looking at the light reflected from the surface, but also looking to the side to get information on the profile of trace gases and aerosol properties in the atmosphere. So thereby, the coverage was only within 6 days, which I think could be similar to the coverage of Flex. So we developed basically 3 aquatic retrievals. One was on quantifying different phytoplankton groups. One is on getting spectral information on underwater light, so how deep is the light penetrating in a certain part of the spectrum. And we also looked at the fluorescence of chlorophyll as an indicator of phytoplankton fitness. And later on, we also applied the data to the newer sensors and also have lately worked on high spectrally resolved data, which are compared to this high spectral resolution rather coarse. So these are the high spatial resolution sensor, DESIS, NMAP, and HICO. And there we have focused mainly on developing atmospheric corrections for these, like terrestrial sensors. But the methods I'm going to show now, which will be based on these atmospheric sensors, there the retrievals run directly from the level 1 data and you account simultaneously while retrieving the aquatic property also for the atmospheric and surface effects. So that is like the suggestions I make here. These novel products from the atmospheric sensors can be split into 3 parts. We have the concentrations not only of chlorophyll, but also of different types of phytoplankton, abbreviated as PFT. We have the attenuation of the light, but not only as a bulk over the whole spectral range, but also for certain spectral domains. And we have the information of the line height of the fluorescence. And we are focusing on aquatic applications on this line height, which is dominated by photosystem 2, so at 680 nanometers, because at least in the open ocean, everything is reabsorbed, which is emitted as light from the second peak, from the far red peak. So why is it beneficial to have retrievals from high spectrally resolved data on phytoplankton groups? There are actually products also from multi-spectral retrievals. These are getting better and better with putting more machine learning, deep learning into it and getting more data for calibrating that in situ data. But from inversions, it's impossible to get at least the taxonomic groups. Size classes to some respect works, but mostly you can only get big and small. So with the higher spectral resolution, we are much more powerful. And also we have shown that the uncertainties can be lower for those products, at least comparing Skiamaki cyanobacteria to standard products. So as a standard product for the diffuse attenuation from the ocean color data, you can get like either you have retrievals which are based on approximations of the blue light. So it's called KD 490. Or it's directly called KD, so the diffuse attenuation over the whole spectral range, KD par, but it doesn't provide any more information than other spectral bands. Lookup tables have been developed based on using the 6 bands from CVERFs and then also getting an estimate how the UV light could be, but actual measurements haven't been made. And with Tropomi now we could show that this is also possible to be retrieved in UVB, in the UVA, and in the short blue. Yeah, and then with the sun-induced fluorescence signal, we can actually see in the hyperspectral data, while the multispectral data, they use, it's called fluorescence line height, they use 3 bands, 1 is close to the peak and 2 are outside of the peak, 1 before and 1 after, to get an estimate of this fluorescent line height. With that, you cannot really account for the shifts in the absorption due to the increasing chlorophyll. Also, if you have a different composition of phytoplankton, this estimate can be quite coarse as you are limited to these 3 bands. So with FLEX, we would think we can make a contribution of the quantification of phytoplankton groups with phycobilins containing groups like the blue algae or cryptophytes. We would think maybe also the spectral diffuse attenuation in the green or red can be retrieved, which is only possible if there's enough light in the water, which means it cannot be in the super oligotrophic areas, but in the more productive areas this should be possible. And with the very high spatial resolution of FLEX, we would expect we could also get products indicating the phytoplankton health based on chlorophyll fluorescence, also in inland and coastal waters, at least larger inland and coastal waters. The core of our retrieval is actually coming from a method called differential optical absorption spectroscopy, which is used a lot for trace gas retrievals from high spectrally resolved data. Just very quickly, so basically we have the backscattered measurement at the satellite, wavelengths resolved. We have the measurement, the unattenuated, so coming from the sun at the top of the atmosphere, which is then approximated by diminishing it by the transmission, which has all the contributions from the ocean and the atmosphere. And the contributions we can differentiate because we have the cross sections for the different oceanic contributions and for the different atmospheric contributions, which would be the trace gas absorption spectra and the phytoplankton spectra, and also the water itself, and everything which is not varying a lot with wavelengths. We are just approximating with a polynomial. By that, we don't have so much to deal with problems due to aerosols or more CDOM or less CDOM. We're really focusing on the oceanic variables we're interested in. And we run the retrieval over a specific wavelength range where we finally also get the best results, but also where we have the strongest absorption features. And to start with the fluorescence retrieval, and this is a quite narrow band way. So we also started to work with Skiamaki, but there have been people from other groups, from NASA and also from JPL, which worked then on GOM2 and Tropomi. So here we look at the wavelength range basically for the retrieval, which is just between 681 and 684. And there we have a very strong signature of a Fraunhofer line, the iron 1 line. And we chose this wavelength range because we would think here the contribution we can see in the filling in of this Fraunhofer line would nearly only come from the fluorescence itself. But you see that still water vapor can have a minor contribution, and we also still would have probably a contribution from the Raman scattering, which is mainly from the atmospheric Raman scattering. So we also use wavelengths which are actually outside of this fluorescence wavelength window. So here you can see that for Raman scattering, we additionally run the retrieval at a wavelength range not too far away from that and look for the filling in these lines. And then we do a lot of radiative transfer calculations to find out what would be the contribution of Raman scattering at the wavelength window we consider in the fluorescence retrieval. And the same we do for water vapor at a longer wavelength range because it is also influencing it. And besides, we were still correcting also for the background radiance. So we look at the strength of the polynomial, and we also, based on the observation geometry, and we can then get more information on the surface reflectance and further improve our retrieval. So the final result is actually now shown on the left side. This is like an average over the 9 years of data which were processed. And on the right side, you can see the retrieval of the MODIS standard product, normalized fluorescent line height. So more or less this Skiamaki product is converted to the same units, and it actually fits well. But you can also see we can actually run the same retrieval also over land. And actually this was the first retrieval to show we can retrieve the red fluorescence also over land and water, and in general, we can retrieve it from space on a global way. So sure, the MODIS looks much smoother with its 1 kilometer resolution opposed to 30 by 60 kilometers. We have a smoother output now if we look at the results from Köhler et al., which uses Tropomi, which has at least 5 by 3 kilometer resolution. But it's not only to justify the results from MODIS. Skiamaki can help to do that. Maybe here we can see the details on the fluorescent line height retrievals in the multispectral datasets. So here you try to get the peak of the fluorescence already quite far out of the peak's position, which is the band 681. Well, you place it at 681 because then the strong oxygen absorption is coming. And then the baselines are between 750 nanometers and 665 placed, so quite far out of the peak. And as I said before, the peak can actually shift a bit depending on the composition of the phytoplankton and also the amount. So the high spectral retrievals give more flexibility to that and also can really look at the peak. And with Flex, I think we will have a really great resolution. We also have now just introduced, I think, at least not as operational products, but in the Snap toolbox for Olgi, you can also produce now a fluorescent line height product from Olgi, and we could compare those. But it would be very interesting to see which actually perform better, Flex or Olgi in this respect. The multispectral or the hyperspectral with similar spatial resolution. The method was also applied to get the fluorescence at the longer wavelength range. And in her thesis, she also looked at the relationship between the two. But as you can see in the open ocean, the signal is noisy and we cannot really retrieve information at the second peak because of the strong reabsorption by water. And I would expect maybe from flex, we should really try in the high scattering water. So if you have a lot of particles, you get also light in the near infrared. If we may be able to also retrieve this signal in aquatic systems, and then with getting both peaks in these turbid inland or coastal waters, we can probably get much further understanding of cross-primary production, but also on physiological limitations of phytoplankton growth due to the relationship of the first to the second peak of fluorescence, which, the first peak is mainly dominated to 95% by the photosystem 2, while in the second peak, photosystem 1 is contributing less than photosystem 2, but much more than at the first peak. Another option, shortly, the other products, I guess the fluorescence is the key thing because it's the key focus of flex as well. We could look at retrievals of the spectral diffuse attenuation. For that, we also look actually at the filling in of Fraunhofer line. So with radiative transfer, we simulate spectra which show at a certain optical condition in the water, which is kind of parameterized with different water constituents. So a certain amount of chlorophyll, a certain amount of degrading particles or dissolved organic matter, and then you simulate how much of the light scattered in the water is actually inelastically scattered and would fill in the Fraunhofer lines. And with that, you can then build up lookup tables. So we take this so-called pseudo-absorption spectra at certain wavelength ranges. These are the three ranges we would run the retrieval. And then we get a scaling factor called vibration Raman scattering fit factor. And we can relate this scaling factor to actually either the light availability at this spectral range, or if we consider it as like the amount how much the light gets attenuated with depth, it's called the attenuation coefficient, the so-called KD product. And with tropomy, which ends at 500 nanometer, we have validated and calibrated retrievals in the UVA, UVB, and in the short blue of the diffuse attenuation. And actually, these have been now also implemented in the tropomy prototype processor called PAL, and the products are daily available and processed. So this is available since this March, since 2025. So this is probably a method we could then adapt to the wavelength range, which is provided by Flex. As I said before, this can only be done in waters where we have enough light in these wavelengths, which cannot be the really clear waters, but more the turbid waters. And for the last thing, I can show you like the differential optical absorption spectroscopy retrievals we run for different phytoplankton groups. Before we were focusing on the wavelength range between 420 and 520 nanometers, and we're able to separate 3 different groups from Skiamaki. We also tested if we can use the wavelength range in the green to actually identify algae which have this peak due to phycobilins, which then not only absorb the light, but at the longer wavelengths emit the light. And this we actually demonstrated for Skiamaki in the open ocean. Again, this is very coarse resolution. This is a testing data set. Because at this wavelengths, the integration time for Skiamaki was even much longer and resulting in much larger pixels. But you can see these belts in the subtropics, in the northern and southern Pacific, and also just north of the equator in the Atlantic, and widespread around the Indonesian islands and in the Indic Ocean. That's like where we also know from other retrievals, there's a lot of cyanobacteria and cyanobacteria which have these phycobilins, and these are the cyanobacteria which actually can fix elementary nitrogen. So I guess on these retrievals, we could explicitly work with Flex, and then we really could go into the inland and coastal waters where cyanobacteria can be quite a threat, and specifically try to retrieve that. But other groups, I don't think would be really possible. So just to summarize my talk, I want to show you that with these differential optical absorption spectroscopy-based algorithms, we call them phytodoas, we could retrieve the marine red chlorophyll fluorescence from the hyperspectral data, and these retrievals actually show very good agreement with the MODIS fluorescence line height product. The approach is quite generic, not only that it can be applied also just over land and also be applied more or less to retrieve the second peak of the fluorescence. It has been shown also to be applicable to successor missions like GOM2 and TROPOMI, and I think it would be also pretty straightforward to implement it for FLEX, and then it would enable also retrievals in the coastal and other waters. And I would propose we could try, in terms of phytoplankton groups, use the inelastic scattering due to the fluorescence of phycobilins and retrieve then the concentration of phycobilins. It's a bit more tricky to get enough data to have a good absolute value finally. And another way would be to also retrieve the spectral diffuse attenuation coefficients in the green or maybe even in the red. With the red chlorophyll fluorescence retrieval, we can also retrieve the second peak, the far red chlorophyll fluorescence, and that could work in high scattering waters, and that might be very interesting and give us more information on the health of the phytoplankton. I think very important is here that, sure, in the past people just use CWIFs, and now still some people just use MODIS. Some only use algae, but it's not only that we only should use the different ocean color sensors together and improve coverage. We should also use the complementary advantage of the different data sets, not only the classical multispectral, but also of these new very high spectral resolve data like TROPOMI and FLEX, and combined with those classical one, but also the high spatial and high spectral resolved ones, but with much less signal to noise ratio. Sensors like DASIS or Nmap. DASIS is not so much available anymore. Prisma and PACE. PACE is more on a larger scale, but also will be very interesting to compare PACE fluorescence retrievals with FLEX and algae. We have some expertise with combining remote sensing data sets for aquatic application from hyper and multispectral data. We had a project from ESA called SynSen PFT, which was on phytoplankton groups and showed quite some success, and I would push that. Still, to directly use the product of aquatic fluorescence of chlorophyll and to obtain a measure of the gross primary production or the phytoplankton health is very challenging. I know it's challenging for the terrestrial community, but you are much less at the noise level of the signal, which is one advantage. Then we have the phytoplankton is so diverse in pigmentation, which makes it very difficult to directly relate the strength of the signal in the fluorescence to actually the productivity. It alters not only with the physiological stage, but also with the composition of the phytoplankton. And models are far less developed, as I can see until now, in the aquatic community than they are for the terrestrial one. But that's the way to go.